Okay, so this week we'll start off looking at section 1.3. Okay, we did the first part of it last time, and now we'll finish it up, which won't take too long, and then we'll look at section 1.4. Okay, this is kind of a review question just to kind of get us back in, like, how do we use the calculator to graph something and then find a window. All right, so it says find a complete graph of 16x minus x cubed. Does anybody remember what I said based on the highest exponent? How you can use that number to figure out how many times your graph could turn? Anyone remember the connection between that number and how many times it could turn? Oh, yeah, twice. It's always one less than the highest exponent. Okay? Doesn't mean it has to turn twice, but it could turn up to 2 times. So when I graph it, I'm going to keep that in mind. All right. So again, press y equals. I'll take in 16x minus x cubed. And what window do I normally start out with? Yeah, the standard one, just to give me a starting point, and I'll go from there. So in terms of finding a complete graph, is that a good window? No. I can see that it's doing some turns, but I'm cutting off the 2 turns. I think I need to adjust 2 out of 4 of the min and max values. Did anybody see what 2 values I need to adjust a little bit? Curtis?
Your y.
Yep. Let's adjust the y min and max. We could try negative 25 to positive 25. Okay, I'm just guessing, but I think that'll be zoomed out enough. You'll see the turns. Barely, but that works. Okay. So for a complete graph, I would say that's good. Nothing? Nope.
Wait, go to your window. I think my window's all messed up.
Did you type that in for your graph?
Yeah, no, that's all right. I think mine's something's up with mine. Oh, that's why.
Okay, anybody else that didn't get a picture? Nothing?
I didn't get it.
All right, and you typed that in for your window? For that, and you got, that's a negative 10. And how about, we got our graph 16x minus x cubed?
Yeah.
All right, let me take a look. Okay, so everybody got that graph now. Okay, so as far as your window, just write down these 4 values: x min max and the y min and max. Now it says determine the domain and range. All right. So domain, what letter does that have to do with? X. So the domain is what you are allowed to plug in. There's only 2 things you've got to be careful with that you're not allowed to do. You can't divide by 0. So that's the first thing. Is any fractions in that equation? Nope. And you can't take the square root of a negative. Is there any square roots? No. So then the domain here is all real numbers. You can plug in any value for x. So you can write all reals. Or, does anybody remember our notation when we put it?
Like an R with 2 lines.
Anybody remember how to write it this way?
Infinity.
Yeah, so negative infinity to infinity. All reals, that's how you write it. Range. Okay, range has to do with y values. Yeah.
For all reals, isn't there like a letter R with 2 lines in it?
That stands for all real numbers, yeah. Or the set of real numbers, yeah. Okay, range, when you look at range, that's how high and low the graph goes. Okay. How high and low is this graph going to go? Any guess? We're only looking at negative 25 to 25, so we know it goes at least that high and low. Yeah.
It's going to go infinite in both directions.
Yeah, it's going to go up and down forever. If you want to zoom out, I just hit zoom 3 and hit enter, so it's going to zoom out a little bit. And now I'm looking at a window from negative 100 to 100, but you can see it's still going. Okay, it's just, this part's just going to keep going up. That part's just going to keep going down. So the domain and the range are the same, always. Okay. Any question on domain and range there? We're going to talk more about domain and range throughout the week. Sometimes people have a little trouble with that. But domain, what are you allowed to plug in for x? Range, what kind of answers do you get for y? If you want to think about it graphically, domain, how far left and right does your graph go? Right? Even though it's not going to the right very fast, it's still drifting to the right slowly, and it will forever. And it's drifting to the left forever. Okay, that's domain. And range, how far does it go up and down? It goes up forever, goes down forever, and it's always connected. Some graphs are not connected. Okay, like if you were to sketch, I'll show you a graph that goes up and down forever that's not connected. Okay, this part you just watch. You don't have to type it in. You go math, number, int x. This is a graph that does go up and down forever, but it doesn't hit every single value in the range. It hits 1. It never hits 1.5. It jumps from 1 up to 2, and then up to 3. Okay? So there's jumps in it. The graph I had before, it's what we call a continuous graph. There's no jumps in it like that. Okay? All right, let's look at this question. Okay, so we have a rectangular pool. Okay, it gives us the dimensions. And around that pool, we're going to put a sidewalk or some kind of border around it. And it's going to be a uniform width, right, all the way around. We know that the area of this region around the pool is 600 square feet. What I want to figure out is, what does the width of the sidewalk have to be? Okay, so what I did is I took all the information in the word problem and I just kind of bulleted the important things. All right, so what do you think would be a good approach for this problem? To maybe try to see this information differently rather than how I have it here. Yeah, why don't we make a sketch, and then we can kind of see what we're working with. So I'm going to start by sketching basically two rectangles, one inside the other. All right, so let's put our first rectangle. And then inside that, I'll put the pool. And that's supposed to be uniform width all the way around. Okay, and the width, what do they tell me, is x. Okay, so I'm going to just mark that as x. I also know the dimensions of the pool. It's 30 feet by 50 feet. Okay, so I've got that. And I know one other thing. The area of the sidewalk. And that was 600. Okay, any questions on the diagram? All right. So first thing I want to do is come up with an equation, and it's going to involve areas of rectangles. But I want to come up with a formula for the area of the sidewalk. So I'm not looking for specific numbers yet. I'm just looking for kind of an idea. Anyone think they know what they could do with the area of these two rectangles to get the area of the sidewalk? What could you do if you had the area of the big rectangle, and then we'll say the area of the pool? That's the inside rectangle. Yeah?
Find the area of the pool and subtract it from the area of the sidewalk.
From the area of the
The whole.
whole thing, yeah. We'll call this the big rectangle on the outside. So find the area of the big rectangle, and then subtract out the pool. And what you'll be left with is the sidewalk. So that's the equation we want to set up. Now we'll start to fill in what we can. Okay, any questions on that idea? So Caitlin, do I know the area of the sidewalk?
600 feet.
Yeah.
600 feet squared.
Exactly. I already know the area of the sidewalk, so I can fill that in. Now, I don't know the area of the big rectangle. So the first thing I need to do is figure that out. Matt, what's the formula for area of a rectangle? Length times width. So can you tell me what the length of that side is? And it's not going to be like all numeric. It's gonna have variables in it.
2x plus 50.
Yeah, exactly. We've got an x, another x. Okay, that's part of it. But then you have this section right here, the 50. So the length of that whole side is 2x plus 50. Any question on that? So that's my length. Times he said we also need the width. Colin, what's the width of the big rectangle? Careful, not times 30, but 2x. Because you have this, and then that all combined together. So how would you combine those three lengths? You wouldn't multiply them, you would add them. So 2x top and bottom plus 30. Now we subtract out the area of the pool. Now they didn't give us that, but they gave us the dimensions, so we can figure it out. David, what do I get when I do 30 times 50? Yep, we get 1,500. You'll see in a second that's not really going to be important because of something that's going to happen. Okay, so now we'll FOIL this out and see what we get. Ian, what's 2x times 2x? 4x squared. And then 2x times 30? 60x, and then 2x times 50. Yep, 100x. So he said 60x plus 100x, that's 160x. Right, now watch what's going to happen in this last part. Colleen, what's 50 times 30? Yep, we get 1,500. And I have a minus 1,500 on the end. Okay, so what happens there? Yep, the 1,500s cancel out. And we're left here with an equation where the highest exponent is a 2. Josh, what kind of equation is that? With the highest exponent being a 2. Remember what you call it? Not sure, Kelvin?
Quadratic.
It's a quadratic. Okay, so when we want to solve a quadratic, the goal is to get it equal to what number? 0. So I'm going to put 0 on the left, and I'm going to put everything else on the right. 4x squared was already there. That's 160x. And then I'm going to subtract my 600. Okay, now there's something I can do here just to make the numbers a little smaller. Gabby, do you see what I could do to make all those numbers a little smaller?
I forgot what it's called, but take 4.
Yeah, you could say factor out a 4 or divide everything through by 4. Same idea. And what do you get if you divide everything through by 4? Oh, Evan?
It would be 40x and then,
If you divide that by 4?
oh no, that would just be x squared and then plus 40x.
Yep.
Plus 120? No. I don't know.
150. And is it plus or minus? Minus. Now, we could try to factor it, but I already know this doesn't factor nicely. So anybody remember how you solve a quadratic if you can't factor? Yeah, Ian?
Quadratic equation.
Yeah, we're going to use the quadratic formula. So before I use it, I just like to write down what I'm going to plug into it. So Hannah, can you tell me what A is in this case?
Would it be x squared?
So it's got to be a number. But it does have something to do with what would be in front of the x squared. 1. And then B would be 40. And my constant, let's see. Okay, so now we'll fill in quadratic formula, see what we get. All right, so we got negative b, plus or minus the square root of, what comes next? You don't remember? Not a squared, but b squared. So that's 1600. It's supposed to be a 1. Minus 4ac. So 4. A is just 1. That doesn't really make a difference. C is negative 150. And all divided by 2a, which in this case is just 1 times 2. Okay. First thing I'm going to do is, I see that I'm subtracting a negative. So I'm just going to cross out the negatives and make them positives. Okay, now I've got negative 40. Plus or minus. What's 4 times 150? 600 plus 1600.
Question, what'd you get the 1600
B squared, 40 squared. So b squared minus 4ac. But then I canceled the minus because it was minus a minus. Okay, now we're just going to type that in, see what we got. Let's round the square root of 2200 off to a couple decimal places. 46.9, we'll say 904. So how many answers does that technically give me? 2. What are we finding again? What did the problem ask us to find? The width of the sidewalk. So what does that mean? What kind of answer are we definitely looking for?
Positive answer.
Positive. So negative 40 minus 46, that's a negative 86 divided by 2. That would be a negative number. So while that negative number is technically a solution to the equation, it's not a solution to our word problem. Okay, we got to use positive numbers. So I'm going to type negative 40 plus 46.904 and divide by 2. Okay, so the width of the sidewalk, a little less than 3.5 feet, 3.452. Any questions on that? Okay, so the point of that problem wasn't really to review area of a rectangle. I'm guessing everybody knew that that was length times width, more the quadratic formula. Okay. No questions? Okay. All right, so next thing we'll look at in this part is called projectile motion. So projectile motion is basically if you throw an object at a certain angle, and maybe it travels like in an arc. And technically the formula for projectile motion is a little bit more complicated than this. This assumes projectile motion would travel in a parabola and over short distances, like even like the length of a football field, it pretty much does. But if you're talking about like launching something from here to Europe, it's definitely not a parabola because of the way gravity works. But this is just a simplified version. So it says that the height of an object after you throw it a certain amount of time later is given by this formula. Now, before I explain what these things are, if you're throwing an object, can anybody tell me one thing that would affect how high it goes? Yeah?
How, the way you throw it, the angle.
Okay, so the angle you throw it at, and what else? Yeah. How heavy it is. What does that have to do with? Gravity. So gravity is represented right there. Okay. That number has to do with feet per second. If you do this in physics, you can see the number -9.8. That's in meters per second. Okay, but we're using feet. So gravity, how hard you throw it. What else?
I was just going to say the force.
The force, maybe we didn't say that. I think we said the angle. Is there anything else that affects, like the height, if you were to measure the height? There's one other thing to think about. Yeah?
The height where you throw it from.
Yes, the height you throw it from. Because if you're throwing it off the top of a building, that's different than if you're at ground level, which would be an initial height of 0. Okay, so V sub 0 is how hard you throw the object. S sub 0 is the initial height. And that -16, that's part of gravity. Okay. When you use this formula, you've got to make sure you're using units of feet and seconds. Okay, so on a test, if I ask you a projectile motion problem, that would not be on there. Okay, you could put that on a reference sheet and use it for this week's test, but somehow you got to know that formula. Okay, does everybody have the formula? All right, so this is example 10 in your book. And it says that we're going to shoot a rocket straight up from ground level. And the rocket has an initial speed of 64 feet per second. Okay, so the 64, that's obviously important. That's your initial speed. Is there anything else in that sentence that's important? It's going to tell us what to plug into an equation. Yeah? Ground level. So what does that mean? Initial height of 0, okay, from the ground. So at what time will the rocket be 50 feet above the ground? Okay, so let's set up our equation first and then see if we can figure that out. Okay, so S, that's just the book, the letter our book used to represent the height. So the height as a function of the time is -16t squared plus, what was my initial velocity again? 64. And the last thing is plus my initial height. But we just said it's ground level, so we don't need it in this problem. And we want to know when this height is what number? 50. So I'm going to set that equal to 50. And what kind of equation do I have? Again,
Quadratic.
it's a quadratic. It's exactly like the last one. Except this time I'm going to show you how to solve it on the calculator. Okay, I'm not going to solve it using quadratic formula. Okay, I'm still going to get it equal to 0, okay, just like I did with quadratic formula. Except now, I'm going to plug that into my calculator. Okay, negative 16t squared plus 64t minus 50. Actually, I'm going to show you how to do it once. I'm going to show you how to do it actually from the step before, and then I'll show you a different way you can do it with what I put a box around. So if you already started typing in negative 16t squared, that's fine. Just keep typing that. But let's do it this way first. Type in just that. Forget about the minus 50 for a second. Negative 16, and you have to use x, you can't use t, plus 64x. So what's in that red box I put on one side. And then I'm going to put what's on the green box on a separate line. Okay, this is one way to do it. Let's put 50 on its own line. Okay, now I need to set my window. X represents time. What's the minimum value you could have for time? 0. That's right before you throw the object. Okay, 0. Now, maximum amount of time would be how long the object is in the air for. We don't know. So I'm going to leave it at 10. If that doesn't work, I'll fix it. But I'm going to assume it's in the air less than 10 seconds. How about my height? Minimum value for the height? Yeah? 0. We don't know how high it's going to go. I'm going to assume, I know it's got to go to at least 50 feet. I'm going to assume it doesn't go over 80 feet. If it does, then I'll just cut part of my graph off and I'll fix it. Okay, let's hit graph and see what it looks like. Okay, there's our object. There's the line coming in at 50 feet. And I want to know when my object is in that section. When is it above 50 feet? So what do you think I need to calculate between the blue and the red curves? What do I need to know? Yeah? I need the intersect. So I'm going to do second calc intersect. And I think, did we do that last week? Intersect, yeah. Okay, I need to keep moving my x value until I finally get it on the screen, which I just did. Okay, I'm going to do the intersection on the right. If someone can do the one on the left, that'll be helpful. So pick a point on the blue curve. Pick a point on the red curve. It doesn't really matter where. Now the guess matters. Wherever I put my guess closer to, that's the intersection that it'll give me. So hit enter on the blue curve, enter on the red curve, and then enter on your guess. And on the way back down, the object is going to hit 50 feet at 2.94 seconds. So when will the object be 50 feet above the ground? Did it say, I'm going to assume that it means 50 feet or higher, because it says 50 feet above the ground. All right. So the rocket will be 50 feet above the ground anytime between 2.94 seconds and, anybody get the other intersection? Yeah?
It says 1.06.
1.06. So any time between 1.06 and 2.94. Now, if it said, when will the rocket be exactly at 50 feet? How would you write that answer? Compared to this one. Because what we just wrote here is when the object is 50 feet or higher. Any time between those two times.
Would it be t equals 2.94 and t equals 1.06?
Right. If it said exactly 50 feet, you would just list the exact times it crosses 50 feet. Yeah, what Hannah just said. Okay. So the next thing it asks is, what is the maximum height? And after how much time is it reached? Okay, so if you want to figure out the maximum height, I'm not sure we did this one last week, but you can do second calc maximum. Okay, number 4. Did we do a maximum last week? No. Okay, the way it works is you got to make sure you're on the blue curve. If you're on the red curve, then just hit your up or down arrow, and it'll move you to the other one. So you start by picking a point that you know is somewhere to the left of the maximum. You hit enter. Okay, pick a point that you know is to the right. And now what you've just done is you've told the calculator to look between those two lines. The guess, again, it doesn't really matter. Just put it between the two dotted lines. Hit enter. And I get that. So let's interpret what that means. So anyone think they can tell me the answer to either part of that question based on what we just found? Yeah, Cameron?
The maximum height is 64 feet.
Yes. So the max height is 64 feet. And this occurs at what time? When does the maximum occur? Colin?
Oh, 2 seconds.
Yeah, at 2 seconds. Remember, the calculator can't actually do algebra. Not this calculator, anyway. All it's doing is trying to estimate it. So if the calculator tells you it's 1.999 and it just keeps repeating, it probably is at 2 seconds. Okay? So maximum height is 64 feet at 2 seconds. Okay, I did say there's another way to do it. I think I'm just going to stick with that way. Okay. So for this problem, you really didn't even need to write this last equation. If you were going to try to use quadratic formula, then yes, you would have. Okay, but we didn't really need it. Okay, any question on that? Okay. Okay, and then the last thing in section 1.3 is what's called a piecewise defined function. Okay. Basically, what a piecewise function is, you can think of taking two graphs, drawing them at the same time, and just sandwiching them together. That's what a piecewise function is. So it's when you really have two or more different formulas that describe what you're trying to graph. You don't have a single formula. You have two or more. Okay, let me show you an example. At the bottom, that's an example of what a piecewise defined function looks like. So the way it works is, depending on the value you tell me, I have to look at these two conditions and decide which formula I should plug into. Right, so Calvin, just give me any number you want. 3. So he gave me the number 3. So I'm going to look at each condition. Is x less than 1? No. He gave me the number 3. So I'm going to look at the next one. Is 3 greater than or equal to 1? Yes, it is. So that means the number that Calvin gave me, I would plug into that to get the answer. Now, let's say instead he gave me the number 0. If he gave me the number 0, I look at the first condition. Is my number less than 1? Yes. 0 is less than 1. I would plug it in here. Okay? So the way it works is you plug it into a different formula depending on the condition. But there's always a place to plug it in. Bless you. It's not like I would say use this formula if x is bigger than 10 and use this formula if it's less than 0. Well, what does that mean for like the number 5? It's not bigger than 10 and it's not less than 0. There's nowhere to put it in. There'll always be a place to put it in. Okay, so any question on how a piecewise function works? 2 different functions. Or you can have more. You could even have 3, 4.
Key requirements overlap?
No, it has to go into one or the other for the type we're going to do. I'm trying to think in general if they ever could. I guess they could, but they usually don't. Piecewise functions, usually it fits into just one formula. And the ones I give you will always work that way. Yeah, it's a good question. Any other questions on just what a piecewise function is? Okay. Now, how to graph it. Okay, we're going to do it on the calculator. And it's very similar to how you would graph a regular function, except you have to do a couple extra things. First thing is you have to put parentheses around what you want to graph. So I'm going to put 3 minus x squared in parentheses. And the next thing I have to do is tell the calculator where to draw that. I only want it to draw that when x is less than 1. So I'm going to put another parenthesis. I'm going to go to x. And then the inequality symbols are under second math. There's all your inequality symbols. So I'm going to pick less than 1. Okay. And now I'm going to do the same thing for y2. In parentheses, I'm going to put in x cubed minus 4x. And again, because there's a condition to it, put that right next to it. Put in x. And now again, to get your inequality symbol, second math. And this time I want greater than or equal to 1. Fourth option. Okay. Questions on that part right there? Okay, I'm going to hit zoom 6 and see if that's a good picture. So notice all of a sudden it just stopped drawing the blue one and then it's tracing along the x-axis. Ignore where it's tracing on the x-axis. That shouldn't be there, but there's no way for us to get rid of it with this calculator. So you should get a picture that looks something like this. Okay, and if I wanted to draw it accurately, the axis shouldn't be colored. It should just be black, just like that. All right. Now, the graph in blue, that was this one. For the graph in blue, do I include the number 1 in the graph in blue or don't include it? Don't include it. So technically on the end here, there should be an open circle because you're not including that endpoint. How about on the graph in red? Am I including the 1 there?
Yes.
Yes. Then there should be a filled-in circle. So that just shows you right on the endpoint, where do you include 1? Because you can't really tell the way the calculator did it. I can't tell if 1 is part of the blue or the red graph. Now I can. It's part of the red graph. And that's it. That's how you graph a piecewise defined function. So it kind of looks like a parabola up to the number 1, and then it just stops. And then it starts to look like this cubic function from 1 on. Okay, any questions on that? Yeah?
I tried to graph it, I get an error.
You get an error? Does it say what kind of error?
Syntax.
Syntax. So what that means is there's a symbol that's wrong. Okay, you could have, like I can show you a syntax error. If I accidentally put in a negative sign instead of a minus sign and hit graph, I get a syntax error. That's one way you could get it. So if you look at what I have typed in, do you see anything that's different between yours and mine? No? Oh, you do? No? All right, let me take a look. Okay, any other questions on that one? Okay, so that finishes up, I think, anything that's really new for today. The last thing we're going to look at is a review of just basic stuff with lines. Okay, slope, y-intercept, things like that. Parallel, perpendicular, okay, some of those things. Okay, so this is one of a couple different ways you can write the equation of a line. This is slope-intercept form. How about Julia? Do you remember what the m stands for in that formula? Yep, that's your slope. And Josie, do you remember what the b stands for?
Y-intercept.
Your y-intercept. Okay, if you already know this formula and you just remember it, you don't have to write it down again, but if it's something you don't know, you probably want to take it down because it'll be on the test. Okay, so a linear function is any function that can be written in that form, y equals mx plus b. Okay, that's called a linear function because when you draw it, it's a straight line. Now, that's covering the case where your line is at some kind of an angle. There is a case where it's horizontal or vertical, okay, and we'll talk about those two really, really quick. Okay, but again, I'm going to try to go through it kind of quick because it's mostly Algebra 1 stuff. All right, so let's see if we can kind of figure out how to come up with an equation for this problem using that formula. So it says 10 years ago, a house was purchased for $60,000. Now the house is valued at $85,000. We're going to assume there's a linear relationship between the time and the value of the house. Find an equation that models this situation. And then after we do that, we'll use the equation to figure out when the house was worth exactly that much money. All right, so I want to focus just on the numbers first. When was the house worth $60,000?
10 years ago.
10 years ago. Let's call that the beginning. Okay, when we bought the house, after no time had gone by, right when we purchased it, the house was worth $60,000. And then how many years later are we looking at in this problem?
10 years.
We're going 10 years later. And what was the value of the house at that point? $85,000. So all we did was basically represent the data in the problem as an ordered pair, where this is time, point in time, and then this is value. Now, what do we have to do a lot of times when you're given 2 points you have to find the what between the 2 points? You have to find the slope. Okay, so to find the slope, you do the difference in the y values divided by the difference in the x values. Okay, so let's do that for our problem and see what the slope is. Okay, so Brandon, what would I subtract in the top to find the slope?
You do 85,000 minus 60,000.
So 85,000 minus 60,000.
Yeah.
Okay, and then Cameron, how about in the bottom?
Just be 10 minus 0.
Just be 10 minus 0. All right, so 85,000 minus 60,000 gives me how much? 25,000, and then we're going to divide by 10, so just take a 0 off, and you get 2,500. What does that slope mean in this problem? What is 2,500 compared to like the house and the time passing? Yep.
That's $2,500 for every year.
Yeah, it's the rate of change in the value of the house. It's going up $2,500 every year. All right, so we've got our M. And just by looking at our coordinates, we should be able to figure out B. What's B in this case? Yeah, Ian?
The value of the house when you first got it.
Right, it's the value of the house when we first got it. It's the point where it crosses the y-axis, which is 0, 60,000. So B is 60,000. Now fill in those two numbers into y equals mx plus b. Let's just do it down here. We get y equals 2,500x plus 60,000. Now, if we want to know when the house was worth 71,250, where would that go? X or y? Y. So 71,250 equals 2,500x plus 60,000. So subtract the 60,000 to the other side. 71,250 minus 60,000 equals 11,250. And my last step, yeah, divide by 2,500. Perfect. Okay, so I'll just hit divide by 2,500. So after about 4.5 years, according to this, the house was worth $71,250. Okay. Any questions on that? Okay. Two special cases of lines, okay, that have different setup than y equals mx plus b. Okay. Horizontal lines have a slope of 0, and vertical lines have an undefined slope. And the first one is pretty straightforward. Okay, if you take y equals mx plus b, and we know that a horizontal line has a slope of 0, if you fill in a 0 for the slope, what's 0 times x? 0. So with a horizontal line, this part gets wiped out, and it's just y equals a number. Okay, whatever the y-intercept is. With a vertical line, that doesn't quite work. Okay, a vertical line has a totally different format. It's x equals a number. And if you ever forget which one is which, just go to your graphing calculator, okay, turn it on, and type something in. Type in y equals 3. See if it's horizontal or vertical. Okay, it's horizontal. And it's a horizontal line right at 3. I can't do x equals on the calculator. I can't show you what a vertical line would look like, but it would just be a vertical line. All right, so now knowing the formula for a horizontal and vertical line, I want to find the equation of the line that would go through the point 2, 3. And the first one I want to do, we'll let it be horizontal. So what would be the equation of the horizontal line that would go right through the point 2, 3? Yeah, it would be y equals 3. That's the line y equals 3 right there. How about the vertical line that would go through that same point? X equals 2. Okay, that's it. Okay, there will be a question on the test with that, so just don't mix up which one is which. Y equals is horizontal, x equals is vertical. All right, so if you're given something like that, 2x plus 3y equals 6, can somebody tell me what the first step would be to get y by itself? Okay, we'd subtract 2x. So we'd have 3y equals, and what would I put on the other side? Yes. Okay, now Mina could have written 6 minus 2x, but if you're going for slope-intercept form, negative 2x plus 6 is the correct order. Okay, and how about Gabby? What would my last step be? Do you remember what letter are you trying to get by itself in slope-intercept? Yeah. So how would you get rid of what's next to y? I like the idea of dividing, but divide by 3. Yeah, divide everything by 3. So now you get y equals negative 2/3 x plus 2. What's the advantage of doing that? Why would you want to take something that's not in slope-intercept form and make it that way? Makes it very easy to find the y-intercept. And what else? Yeah, Colleen? Yeah, makes it very easy to graph because now if you know the y-intercept, you go down 2 and right 3, use your rise over run, and you can graph it. Okay, so that's definitely important to know. Point slope form is another way to write the equation of a line. Okay, that's helpful if they give you a problem and say, I want you to find a line with a slope of, say, a half going through the point 5, 6. This is very helpful to do that. It's y minus y1 equals m times x minus x1. And you fill in, if you're going to do the kind of problem I just said, you fill in for 3 things. The y1, the m, the x1. You fill in the 3 things I just circled. All right, so let's try one like that. So I want you to find the equation of a line where the slope is a half, and I want it to pass through the point negative 2, 3. Okay. How about David? What's m in this case? Yep, 1 over 2. I'm just going to fill that in first. Wyatt, what's y1? Yep, So we're going to fill that in. And Mina, what about x1? -2. So what happens when I plug in minus -2? Becomes a +2. Okay, now technically if they said find the equation of the line, you've done that. That's the equation of a line. It's not in slope-intercept form, but it answers the question. If they wanted it in slope-intercept form, you would distribute out the 1/2. And then what would you do with the 3? You would add it. +4. That's another answer to this problem, this time point slope form. And I'm going to show you one other way you could write it. What if I didn't want any fractions? What could I do to everything here to get rid of all my fractions? Yeah?
Multiply by 2.
Yeah, I could double everything. 2y equals x plus 8. And the other thing I could do is put everything on one side, kind of like you're solving a quadratic. That's another way to write it. Okay, so what I'm doing is just showing you different ways, because on the test there will be a multiple choice question similar to this. And maybe you'll get that is the answer, but I might rewrite it this way or this way. It's just rearranging it different ways. Okay, any questions on that? All right, so then, yeah, last two things. So parallel lines and perpendicular lines. If lines are parallel, can someone tell me what do you know about them? If they're parallel. Colin?
They'll never touch.
They'll never touch. And what does that mean in terms of like slopes and intercepts?
They're running along one of the same axes, whether it be x or y.
Can you describe that in terms of slope? If they never touch?
They have the same slope.
Exactly. Same slope, but they also have to have something else. Because I could name two lines with the same slope that are not parallel. Okay, so that means they would have to have different y-intercepts. Because if you had same slope, same intercept, it's the same line. Okay, so parallel lines, same slope, different y-intercepts. How about perpendicular? Does anybody remember what the slopes have to be for perpendicular? Opposites and one other thing. So like positive, negative. They also have to be one other thing besides just opposites. They have to be opposite reciprocals. Okay, so perpendicular lines, slopes are opposite reciprocals. Okay, so the kind of question you would see on this would be very similar to the problem we just did. It would say something like, find an equation of a line. This time I want it to be parallel to that line. And the new line that I find, I want it to go through the point 1, -2. Well, if you want to find a line that's parallel to that, what's the first thing you have to know about what I circled? Yeah, you've got to find the slope of 3x minus 2y equals 1. So the first thing I would do, like we just did, get y by itself. So we have -2y equals -3x plus 1. And then divide everything by -2. You don't even really need to simplify. All we want to know is the slope. What's the slope of that line? 3 over 2. Now for my new line, what's the slope going to be of my new line? It's going to be 3 over 2 because we said parallel. So same slope. And what's the coordinate that I said it has to pass through? It has to pass through 1, -2. So now you've got a slope, you've got a point. It's exactly like what we just did in this problem. Here's a slope, here's a point, find the equation of the line. Okay, so from there, I'm not going to do this. We just did something like that in the last one. Okay, so now, find equation of line. What if you wanted a line that was perpendicular? What would you use for a slope instead of 3 over 2? You'd use -2 over 3. Yeah. And you do the same thing, just with a different slope. So any questions on finding an equation of a line parallel or perpendicular to another line? Okay. All right, so then the last thing is graphing a linear inequality. So there's really 2 steps to graphing an inequality. First thing you have to do is graph a line. And you have a choice whether you make your line solid or you make it dotted. The way you know which line to use, solid or dotted, you just look at your symbols. If the original problem has the equal to's underneath the less than and greater than, you make it solid. If it doesn't have the equal to's, you make it dotted. And then the second step, I kind of built it right into what's above. You either shade above this line or you shade below. You shade below for these 2 symbols. Less than, think less than is smaller, below. Greater than or equal to, shade above. Okay, so we'll finish up with an example of that. All right, Ezekiel, can you tell me what I would want to do first to graph that? Yeah, there's different ways you can do it, but that is one way. Get it into slope-intercept form. And what would your first step be? Perfect. I'm going to move over the 2x. So 3y is less than -2x plus 4. And can you give me my last step? Divide by 3, 3, and 3. All right, so not the nicest line to graph. 4/3, that's 1 1/3. So that's my y-intercept. Close enough. And then from that point, how does the slope tell me to go from that point? What direction? Down 2 and to the right 3. So down 2 to the right 3. I'll just try to do it one more time. Down 2, right 3. Close enough. Would this one be a solid line or a dotted line? Dotted? Yep. So let's put in a dotted line. Probably about like that. And would I shade? It's okay. Shade above or shade below? Yeah, shade below because it's a less than. So we went through a lot of different things there, but I'm hoping most of that was review, y equals mx plus b, and shading and stuff like that. All right, so the homework tonight, a little bit on the first part we did with the functions, okay, and then on the second part, page 42, that's the stuff with slope, y-intercept, things like that. So on page 31, it says 32 to 36, 45, 50 to 52, and 55 to 57. And then page 42, it's 2, 8, 11, 16, 17, 20, 24, 27, and 32, 44, 77.